Introduction to Statistics, Chapter 8, Sampling Distributions, Section 8.1, Distribution of the Sample Mean. A sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. The sampling distribution of the sample mean, x bar, is the probability distribution of all possible values of the random variable x bar computed from a sample of size n, from a population with mean mu, and a standard deviation sigma. The mean and standard deviation of the sampling distribution of x bar. Suppose that a simple random sample of size n is drawn from a population with mean mu and a standard deviation sigma. The sampling distribution x bar has a mean mu sub x bar equal to mu, the mean of the population, and the standard deviation sigma sub x bar is equal to sigma, the standard deviation of the population, divided by the square root of n, the sample size. The standard deviation of the sampling distribution of x bar, sigma sub x bar, is called the standard error of the mean. If the distribution of the population is known to be normally distributed with a mean mu and a standard deviation sigma, then the sampling distribution of mean x bar is normally distributed. So if the population is known to be normally distributed, the sampling distribution of the mean will also be normally distributed. Now, in case it's not, we have the central limit theorem. Regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. So as we increase the size of the sample, no matter what the shape of the population was, it will become approximately normal. Now, if the distribution of population is unknown or not normal with a mean mu and a standard deviation sigma, then the sampling distribution of the mean x bar is approximately normal provided the sample size is greater than or equal to 30. So 30 is the magical number. If your sample is 30 or more, then you can assume that the x bar distribution is approximately normal and use the normal distribution for it. Now, using StatCrunch to find probability for a normal distribution of x. We've done this in the previous chapter. You click on Question Help at the top right of the problem to open StatCrunch. You click Stat on the top menu, highlight Calculators, click Normal. Enter the value for the mean, which is mu in this case. Enter the value for the standard deviation, sigma in this case. Choose correct inequality, less than equal to or greater than or equal to for your problem. Enter x value, x in this case, and click Compute. We've done this in a previous chapter. Now, how's this going to change when we're talking about an x bar distribution? Well, if we have a sampling distribution of x bar, we're still going to open it up the same way. We're going to open StatCrunch, we're going to highlight Calculators, click Normal. But now, this time, when we enter the value for the mean, we're going to enter mu of sub x bar for the mean. And for the standard deviation, we're going to enter sigma sub x bar. Choose the correct inequality, less than equal to, greater than or equal to. Enter, this time where it says enter x value, you're going to enter the x bar value. And click Compute. So basically it's the same thing. Instead of using mu, sigma, and x, we're going to use mu sub x bar, sigma sub x bar, and x bar. Now, let's look at how this is used in the real world. Why does your doctor sometimes require a second test, and how is it used? Well, let's look at an example here. Let x be a random variable that represents the level of glucose in the blood, milligrams per deciliter of blood, after a 12-hour fast. Assume that for people under the age of 50 years old, x has a distribution that is approximately normal, with a mean of mu equal 85 and an estimated standard deviation sigma equal to 25, based on information from diagnostic tests with nursing applications, edited by S. Loeb Springhouse. A test result of x less than 40 is an indication of severe excess insulin, and medication is usually prescribed. So let's look at what happens here. So your doctor has you take a test. You take a single test. So this is just a normal distribution because the population is normally distributed, or approximately normal. So it's a single test, so we're going to use mu, we're going to use sigma, and we're going to use x. So in this case, mu is 85, sigma is 25. We're going to look for the probability x is less than 40. Okay, so let me end this. And if we go to StatCrunch, what we're going to do, click on Stat, highlight Calculators, click Normal. Now, we're going to want to put the mean in. So in this case, the mean was 85, standard deviation was 25, and we wanted less than 40, which is the same thing as less than or equal to 40 with the normal, and click Compute. So we get 0.0359332. Okay, so now this brings us to this case. I rounded off to 4 decimal places. So what's that mean? 3.59%. Now, in this case, that 3.59% means that 3.59% of the population who takes this test ends up below 40. Okay? It also means that there is a 3.59% chance you do not have it. Okay? That this would be incorrect. So, what happens is your doctor now asks you to run a second test. So, suppose the doctor decides to run a second test a week later. What is the probability average of the two tests, x bar? Now we're talking an x bar distribution, the average. So x bar is less than 40. So the sampling distribution will have 2, the size will be 2. Now mu of x bar is equal to mu, which is 85. But now sigma sub x bar is going to equal sigma divided by the square root of n, which is going to be 25 divided by the square root of 2, which is approximately 17.68. And what are we looking for this time? We're looking for the probability x bar is less than 40. We're looking for the average to be less than 40 of the two tests. We're not just doing a separate test by itself. We're averaging the two tests. So now, if I go back to StatCrunch, this time the mean is still 85, but now the standard deviation is now 17.68 approximately. So I'm just going to put 17.68 in. And I want x less than or equal to 40 again. The only difference here is the standard deviation has changed when we average. So if I click it, now I've got this probability, 0.00545999. And if I come back over here and I round that off to 4 decimal places, now what's that turn? That's a 0.55%, which is about a 0.5%. Okay, so if you run 2 tests, now we've cut the percentage of people that end up less than 40 greatly lower. That's only about a 0.5% compared to 3.5% on 1 test. And also, the doctor has less chance of being wrong. You know, he only has a 0.5% chance of being wrong. Now, this is just blood work, but what if it was some severe disease? You know, the doctor doesn't want to be wrong, so they always want to run that second test. And you notice when you run the second test, the probability dropped drastically. Okay. Now, let's suppose the doctor decides to run a third test a week later. What is the probability the average of the 3 tests, x bar, is less than 40? So now, sample size is n equals 3. We're doing 3 tests. So mu of sub x bar is mu, which is 85 yet. Sigma of x sub x bar is equal to sigma divided by the square root of n, 25 divided by the square root of 3. Now it's come down to 14.43. And I want the probability x bar is less than 40. So I would go back to my StatCrunch. And this time, I would change the standard deviation to 14.43. Click Compute. And I end up with this answer, which you notice is even lower. So now if I come back over here, I have my 3 possible answers. If I run a single test, I got 3.59%. If I run 2 tests, 0.55%. If I run 3 tests, now I'm down to 0.09%. That is very, very small. Now, the situation here is there is a big difference between 1 and 2 tests. 3.59% and 0.55%. There's a big difference. So insurance companies will only usually pay for 2 tests, because anything beyond 2 tests is overkill. So the insurance company will pay for 2 because they want to be sure that things are accurate. So the second test, they understand statistics. All right. Now, this brings us to the end, I believe, of section 8.1. Okay. So this was sampling distribution of X bar.